In this section, we're going to talk about the introductions of stress. The stress in concept is the force per unit area. And to talk about this stress, we need to know the two quantities. And one quantity is force, and the second quantity is on which area and the force is applied. And in terms of a type of the loading or force, we have two here, and one is called the normal loading. The normal loading basically is the direction of the force is normal to the surface area it's acted on. For the shearing loading, basically the direction of the force is in parallel to the area it's applied to. We're back to the very special case called the three-dimensional axial loading, and basically the loading can be this one indicating is the application of normal loading in three directions, and the directions of the loading can be pointing to the surface or can be point away, okay, and either directions, and depends on the applications. So this page we talk about the stress as the first place. So basically in concept, the magnitude of the stress is simply very straightforward. You simply pick the force and which applied and to the area, and then the stress is defined by the force per unit area. For example, if you have force 10 Newton, and apply to an area, and the area, for example, 1 millimeter square, then basically this is the stress, and we call the stress that have a magnitude 10 Newton per millimeter square. Okay, and in this way you can see the stress and pretty much has the similar idea to pressure. Pressure also is the force per area. So here the stress, we have the unit, for example, Pascal per square inch, and the pound per square inch, or Pascal. Pound per scale is Newton per meter square. And in next slide we will have more detail about this one. In the entire ES331 class, we will learn how to calculate the average stress. And here I would introduce additional terminology, the average stress. And here I'm going to tell you what is that and why we are doing this. Usually from here is this: when we apply the loading usually is the pointed. So which means nearby where the location, the point applied, you should expect something like needle poke your skin, and locally you will feel very hurt because the stress there is pretty concentrated. And if you pick any cross-sectional area and that is farther away from where the loading applied, for example, we pick this section, and looking here you can see the uniformity of the stress is pretty much flat there. So in this class, our concerns and as a first learning lessons, we don't consider this called the stress concentrations. We don't consider this because this involves quite a bit rigorous considerations and calculations. But again, as a first class, we just want to learn how to calculate the roughly the average stress. Okay, so basically whatever the stress F here, we apply, divide by the cross-sectional area A, and this average stress simply is F divided by A. Okay, and here we use a symbol sigma for stress and the same thing here again, that is repeated. So again, if we pick a cross-sectional area that is very far away, from the loading where applied, then basically in that cross section we can estimate the average stress. Basically again, that is F divided by A, and then sigma equal to, and sometimes the people using the average and to emphasize, sometimes not. In this class, again, unless we otherwise pointed, then all the stress calculations are based upon the average sense, and keep this in mind. So we move on to the next page here. So this page we give the formula. So here is the way how to calculate stress. First one, you determine the loading, the magnitude of the loading, whether that is normal loading or that is shear loading, and divide by the cross-sectional A, and that divide by which cross-section you're interested. Okay, so this is about the magnitude of the stress. And here we talk about the unit of the stress, and there's two kinds of unit. Either you want to use the SI unit, that means force as Newton and area as meter square or millimeter square. And in these systems, we define the Pascal as 1 Newton per meter square, and K means 1,000, and that means 1,000 Pascal. M means million, so 1 MPa meaning 1 million Pascal. G is giga, so that 1 GPa is 10 to the 9 Pascal. And most of the time in mechanics material, and we have used MPa quite a bit often, because that is often the scale of the stress being commonly seen in the most of the loading applications. So you will see the MPa quite a bit often. MPa again, that is 1 million Pascal. And if you do the unit conversions, and from here you can see 1 Newton per meter square, and 1 meter square, and 1 meter equal to 1,000 millimeters square. So basically here is equal to, here we can cancel this, and that is 10 to the 6 and millimeter square. Okay, so under these situations, from here, and over and meter equal to this. So from here you can arrive is 10 to the 6 m over n meter square equal to n millimeter square. So from here you can see 1 millimeter square equal to 1 MPa. Okay, so that is the unit conversion here. On the other side, if we're going to use the English unit, for example, using the force as the pound, okay, the force using pound as a force unit, and then per inch square is called the pound per inch square, pound per square inch, PSI. So that is the definition for this. And K means 1,000, and again, in traditional mechanics response to regular loading, KSI is pretty common scale we will experience. So you will see this KSI pretty much often and in this class. Okay. Again, the type of the stress. When we talk about the stress, you need to know is the magnitude. Okay, so we have calculated magnitude equal to the magnitude of the force divided by whatever the area applied. So for the stress here, we talk about is the first one is we talk about the magnitude calculations. The second one is called the type of the stress. And again, for the normal stress is induced by normal loading. The loading is perpendicular to the area is applied. So for this one, we call it the normal stress. normal loading induced stress is called the normal stress, and we use sigma to indicate and to symbolize the normal stress. So for this example, the normal stress in average, again, we in ESG 31, we determine is an average stress. Okay. And so for tensile stress, we define as this. For these illustrations, and the tensile, that means has the forcing applied in the tendency to stretch the material. For that case, we call the tensile stress. On the other side, if we revert the direction of the loading to compress this material, then corresponding calculated stress called the compressive. Sign convention. Here in mechanics material, we have sign convention. We define the tensile stress as positive. We define the compressive stress as negative. And for sign convention, there's no reason to explain. We just follow it. The second type of the stress is called the shear stress. Shear stress is where you can see if we will pick this cross section here and taking the free body diagram, basically here, that is a section we pick from here. And on that cross sections, and that is a reaction. This is a reaction which is a force. From here you can see this force is parallel to the area, as opposed to this case the force is normal to the area. So for this case we call it is called shear stress. The shearing force induced stress called shear stress, and for shearing stress sometimes we call it shear stress or shearing stress, and we're using tau. And in this class we're using sigma for normal stress, we're using tau for shearing stress. That's simply, again, that's a symbol use. Okay. And here is a no sign convention for tau, and again in magnitude the average shearing stress basically equal to magnitude of the loading divided by whatever the area here, PA over A. If you really want to pick it, and so you can indicate on this area the shear stress will be this is cross section, and the shear stress will be in this direction, in the same directions of the loading. If you want to be picky, then you can identify the direction as well. Okay, so usually the stress composed of the magnitude and type and then the directions. Okay, so for example, direction in terms of normal stress is told by tensile or compressive. The direction of the shear stress, you can just indicate it on any graph you've been working on the problems. Okay, something like this one. Again, for the features of the stress, there's three things. One is the magnitude, one is type, one is directions. To completely describe a stress, you need to provide the three informations, okay, to make that complete. So here in this section, we start